Alright, we saw in the last video that based on the stoichiometry, the rate of the reaction measured versus various reactants or products might give you different numerical values. So essentially what we want to do is we want to sort of standardize our discussion of kinetics and talk about the rate of a reaction. The rate of the reaction. From here on out, whenever we refer to simply the rate of the reaction without specifying a reactant or product that's appearing or disappearing, we're talking about the rate based on one of the reagents whose stoichiometric coefficient is 1, or what it would be if you divided by the stoichiometric coefficient. So we're sort of standardizing it. And what scientists have discovered is that if you look at a reaction experimentally, you can form an equation which governs the rate of the reaction, and with just a few variables we see exactly the same equation every time. So for example, if we take the generic reaction A plus B, my lowercase letters are going to be coefficients, goes to products. If I look at this reaction experimentally, I will find that the rate of the reaction follows the equation. I will find this equation governs the rate of this reaction. I have the rate is equal to some constant. This K is called the rate constant, and it has to be determined experimentally, times the concentration of my two reactants raised to some power. This power is not the stoichiometric coefficient. Notice I did not write little a and little b. M and N are called orders of the reaction, and they have to be determined experimentally. But what we find is all reactions follow this pattern, again with just a few variables. Now what we find for these orders is that typically they are either 0 or 1 or 2. They're small positive integers, or they might be 0. It does get more complicated than that. If you go on and take a class in physical chemistry, you'll talk about how it can be way more complicated than that. But by and large, in general chemistry, we stick to small positive integers for our orders. And so that's what we see as far as what M and N would be. So K is called my rate constant, and it's experimentally determined. M and N are the individual orders, and if I add all of my orders, I have what's called an overall order. The beautiful part about this equation is if I know experimentally what my rate constant and my orders are, then I can predict what the rate of the reaction would be given various initial concentrations of my reagents. And that's kind of useful. There are other uses for it. We'll talk about it as we develop the material more. Just a little vocabulary here. Once we have written this equation, this experimentally determined equation, we'll have some numerical values for our constants and our orders. This is known as the rate law. This is the rate law. It's called a law in chemistry because it tells us what happened. It does not explain why this happens. It simply tells us what is happening for this reaction. There's a lot to be determined experimentally here, but this is known as the rate law. Let's talk about how we would figure out what the orders are, or how we would predict what the orders are. What effect does the order have? And to do that, I'm going to bring in an image that we'll work on. Alright, what I'm doing in this table is, first of all, I'm simplifying our reaction. Let's say that my reaction is simply A goes to products. Only one reactant. Let's narrow it down so that we can look at how this behaves. My A going to products is the reaction that I'm monitoring. Let's say I run 5 trials, 1, 2, 3, 4, 5, and I'm going to change the initial concentration of my reactant A, and let's say I'm looking at an initial rate, and I have a stopwatch or other method of measuring the rate of the reaction in the laboratory, and so I'm able to numerically get a value for the rate of the reaction when I start this reaction with a 0.01 molarity concentration of reagent A. And let's say that my answer is that the rate of my reaction when the concentration of A is 0.01 is 0.37 molarity per second. If I have been told that this reaction is first order, What that means is that my rate is equal to K times the concentration of A raised to the first power. That's what this means when I'm told that it's first order. That means if I change the concentration of A, as I did from trial 1 to trial 2 by doubling it, my concentration of A is now times 2. Numerically in this equation, I would now have twice the concentration of A, but it is to the first power, which means that the rate would also go by 2. That means that the rate of the reaction when my concentration is 0.02 should be 0.74 molarity per second. I'm not going to keep writing that. Now, that's if I know that it's first order. I should find that, and I can check that experimentally. We can carry this a little bit further. Let's say that I want to predict what the rate would be if I change the concentration to 0.06. Well, if I change the concentration of A to 0.06, what I should find experimentally is that the rate would be 6 times what it is from this first trial, because I changed the concentration by 6. What I should find experimentally, let me not worry about sig figs so much, is that the rate should now be 2.22 molarity per second. I would have also gotten the same answer if I'd said, well, from this trial to this trial, I'm actually going up by 3, so from this rate to this rate, I'll go up by 3, and I would get exactly the same answer in that case. Let me go ahead and extrapolate this quickly. If I change the concentration to 0.05, I have gone up by 5 for my concentration, so my rate should go up by 5. If I change the concentration to 0.2, I have several options here to look at the change, but let's go from 0.05 to 0.2. That concentration went up by 4, and so my rate will go up by 4. So what we have here is we have a table of expected rates based on the fact that you are told that this reaction is first order. So this is how the table works. Now let's look at a different order to see how that works. All right, I have a new table, and we're talking about a new reaction. This has to be a different reaction because we're going to change the order. A reaction's order is its order is its order. It's determined experimentally, and it is a property of that particular chemical reaction. So now I have a different reaction. A goes to products, and let's say that I'm told for this reaction that it is second order. In the second order reaction, very similar to the last one, I'm going to run a trial where the concentration of A is 0.01, and I've got my stopwatch, and I measure that the rate of this reaction happens to be 0.45 molarity per second. What happens when I change the concentration to 0.02? Now I'm doubling the concentration of A, but remember we're talking about a second order reaction. That means that the rate of this reaction is governed by the equation rate equals K times the concentration of A squared. That 2 in the exponent is my order. I'm told it's second order, something that's determined experimentally. And so if I have a second order reaction, this is the equation that governs it. This is known as the rate law for this equation. That means if I take the concentration of A and double it, the rate is going to change proportional to A squared. So from here to here, the rate will go up by 2 squared. The times 2 is because I doubled it, because I doubled the concentration of A. The squared is because it is second order. And so if I calculate what this would be, I would see that my new rate would now be 1.8 molarity per second. Going in a similar fashion, if I change the concentration of A to 0.06, what I've done to the concentration of A is I've multiplied it by 6 from my starting trial. That means my rate will go up by 6 squared. The times 6 is because that's what happened to the concentration. The squared is because it's second order. So my rate, I should expect to see a rate of 16.2 molarity per second. I'm not worrying about sig figs. I'm just putting my answers for my calculator. Quickly, we can see that if I go to a 0.05 concentration, I should observe based on the fact that my concentration went up by 5, that the rate will go up by 5 squared. So I should see 11.25 for the rate of that reaction. And if I change the concentration to 0.2, I have several places that I can take this from. Let's just go from here. Between 0.05, raising it up to 0.2 molarity, I took my concentration up by 4, which means my rate will go up by 4 squared. So I expect to see the rate at 180 molarity per second. And that's how a second order reaction would behave. Let's look at another one. Alright, new table, new reaction. I'm looking at a totally different reaction, but again it has the format of A goes to products. I am told in this case, I'm looking at a third order reaction. My third order reaction means that my rate law, the equation that governs the rate of the reaction, will be rate equals K times the concentration of A cubed. And so let's look to see how I would expect this to behave. If I change the concentration from 0.01 molarity to 0.02 molarity, that means I am doubling the concentration. If my initial rate was 0.69 molarity per second at a concentration of 0.01, then I would expect the rate to go up by 2 cubed. The times 2 is because I'm doubling the concentration. The cubed is because it is third order. So I would expect my new rate to be 5.52 molarity per second. If I change the concentration to 0.06, that means that I went up by 6 for my molarity, my concentration. Then I expect the rate to go up by 6 cubed. So I'm looking at 149.04 molarity per second. Again, I'm not worrying about sig figs, I'm just writing the values down. Let me do the others quickly. Beating dead horses here, although there are no horses and they certainly aren't dead. If I go up by 5, I'll go up by 5 cubed. And lastly, if I go from here to here and it's times 4 on my molarity, this will be by 4 cubed. So we see the behavior based on a third order reaction. We have to be given that information at this point in our lives that we're looking at a third order reaction to be able to make these predictions on the rates. This is how the rate changes as you change the concentration of one reactant based on what the order of the reaction is. Let's just look at one last example. In this one last example, let's look at what would happen if we're told we have a zeroth order reaction. If A goes to products and you are told it is zeroth order, what that means is that my rate law is now rate equals K times A to the zeroth power. We do see zeroth order reactions sometimes, and zeroth order means that the concentration is raised to the zeroth power. Now what happens mathematically if you raise anything to the zeroth power? That anything raised to the zeroth power is 1. And so rate is simply equal to this constant. So this one's actually easy if you're told that you have a zeroth order reaction. What that means essentially is that the rate doesn't change if you change the concentration of A. The rate stays constant. And so this one is very easy. It doesn't matter what the concentration of A is. The rate stays at 0.23 molarity per second, even as you change the concentration of A.